Alright, so in this video we again want to chat a little bit about how we can use that previously constructed no-show table to slowly transition into one of these proofs that are written up as a paragraph. So in this situation we're going to be looking at this statement that says if n is an even integer, then n squared plus n plus 1 is going to be an odd integer. When you look at this proof, you're going to see a whole bunch of similarities between this and the one that we first started with, this notion of if n is odd, then n squared is also going to be odd. And the reason for that is the overall structure of the actual statement is going to be very similar. I'm assuming something about a particular value. In this case, that assumption is going to be about the parity, whether or not it's going to be even or odd. And my overall outcome is going to be talking about something being even or odd. So all of these proofs that involve kind of even and oddness are all going to be structured very similarly. What you're going to do is you're going to start off with this blanket assumption that n is going to be even, or n is odd, or whatever one you're working with. In this particular situation, I'm starting off with n being an even integer. So that statement actually goes ahead and tells the reader right away that for the rest of this proof, n is going to be some even integer. It's a very general even integer. It's not making any assumptions about what n actually is. All I know is that n is going to be even. What we're going to do next is then switch from just this general notion of being even to really digging into the structure of what does it mean to actually be even. In this case, we really use this fact that n looks like 2k. When we go into the actual computational side of this thing, we're going to see that that additional 2 becomes super important. That's actually the 2 that comes out of this huge expression to see that this expression looks like 2 times something plus 1. So that's what that step is going to do. I'm going to make this claim that since I know n is even, I know there's going to exist some other integer k such that n equals 2k. Next is going to actually be that little statement that's going to bring about all of this kind of messy algebra computation. So in this situation I said, using algebra we obtain blah 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 blah. We could also said, expanding blank blank we have the following. Any of those kind of lead-in statements that are going to at some point in time let the reader know that there's this huge block of algebra that's about to happen. So kind of hold on tight and make sure all those steps seem to kind of pan out as they should. So in this case, I just use this kind of blanket expression saying using algebra we obtain. I actually like the phrase expanding a little bit more than that, but in this case we're actually just using algebra. What's going to happen is I'm going to restate this expression n squared plus n plus 1, substituting in that 2k for all of those little n's, doing that actual squaring computation, ultimately trying to make this thing look like 2 times something plus 1, because that's what this notion of being odd is all about, is it looks like 2 times some other random integer. In this case, all of that's going to be added to 1. This idea that it looks like an even number plus 1. So now what I want to do is I actually want to tell the reader that this expression 2k squared plus k is in fact going to be that other random integer that I'm looking for. And the idea is that I've not done anything to break the kind of fact that k started off as being an integer, and now I'm doing this kind of extra computation. That new thing is still actually going to be an integer. All I'm doing in this case is I'm taking that k, I'm squaring it, which is still going to be an integer. Multiplying by 2 is going to leave me in the integer world, and then adding another k is still going to leave me as an integer. All of those things are just going to be encompassed in this idea of the closure of the integers. I can take any number of integers that I want, I can add them together, I can multiply them together, I can subtract them, I can do any of those operations that I want to, as long as I'm not doing division or taking square roots or any of those things that are going to leave the world of being an integer. So in this case, because I know I haven't done any of those, I can state this fact that by the closure of this set of integers, using this addition and multiplication, I know that 2k squared plus k is in fact going to be an integer. And then at the very end of this, I can kind of wrap things up and say, therefore we have that n squared plus n plus 1 is going to look like 2 times something plus 1, where that something, in this case L, actually is an integer. And you might as well go ahead and tell people exactly what L is going to be. In this case, L looks like 2k squared plus k. And then at the end of the day, just finish this off by saying n squared plus n is in fact going to be an odd integer. So that last little kind of couple sentences, I guess, is really just this connection between this thing looks like 2l plus 1. I really want to drive home that point that L is in fact going to be an integer, and then reference back to this notion of what does it mean to actually be odd. So at the end of the day, you get this kind of somewhat formal proof that's going to indicate to everybody